Hello, today we are going to learn about the membership algorithm for context-free grammars. This membership algorithm is also called as CYK algorithm, named after its inventors J. D.H. Younger and T. Kazami. The first letters were taken as the name of the algorithm. So this algorithm is basically to check whether a given string is a member of the language generated by the given context-free grammar. The prerequisite for this algorithm to work is that this algorithm can work only if the grammar is in Chomsky normal form, that is CNF form. So a context-free grammar is said to be in context-free Chomsky normal form if all of its productions are of the form either A gives BC or A gives small a. That is, exactly two variables can be on the right hand side. A gives BC or only a single terminal on the right hand side. So if the given grammar is if all the productions are of this form, and when a string is given, we can say that whether the given string is a member of this algorithm, a member of this context-free language or not. Now we can assume a grammar in CNF form and a string, say W is equal to A1, A2 up to AN. Now in this algorithm what we need to do is we need to define the substrings of the given string, and we need to find a set of variables that can derive that substring. Substring means, for example, let's say W is equal to AABBB. This is a string given, and the positions of the strings are 1, 2, 3, 4 and 5. Now the substrings can be something like this. So if I want to find a substring from position 1 to 3, W1 3, then it is AAB, or W35 then BBB. Okay, so from this to this. So like this we can have many substrings, like if I say W11, then that is from position 1 to 1, so this is equal to A. And if I say W15, then it means that so the entire string can be taken as the substring. So in this algorithm we are going to construct a triangular table, and table filling method is used to solve this. Let's see using an example. Let's take this context-free grammar. And let's take the string as now we can see that in this this grammar follows Chomsky normal form. So all these productions are having either two variables on the right hand side or a single terminal on the right hand side. So this is in Chomsky normal form, so we can proceed with this using the CYK algorithm. Now we want to construct a table in that each row corresponds to one particular length of the substring. So the top row, so we have a string of length 5. So the top row is going to contain substrings of length 1. So the first cell is W11 and then W22. That means 1, 2, 3, 4, 5. So W11 represents the first substring of length 1. W22 represents substring of length 1 from position 2 to 2. So similarly W33, W44 and W55. So the first row corresponds to substring of length 1. The second row corresponds to substring of length 2. So the substrings are, we can take it as AA, then AB, BB and BB. So these are all substrings taken in sequence from the given string. So that is 1, 2, 2, 3, 3, 4, 4, 5. So all these corresponds to this second row. So W12, W23, W34 and then W45. Now the third row corresponds to substring of length 3. So 1 to 3 of length 3, then we can take this 2 to 4, then we can take 3 to 5. So there are 3 substrings of length 3. So W13, W24 from 2 to 4 and then from 3 to 5, W35. Then the fourth row corresponds to substring of length 4. So we can take 1 to 4 and then from 2 to 5. So W14 and W25. Finally, the entire string is taken as the substring W15. Now we'll see how to fill this table. So the grammar is given as S gives AB, A gives BB or A, and B gives AB or B. Now we know that each cell of this table corresponds to a substring of the string. So we need to find a set of variables that can derive the substring. So first let us take this cell. So W11, so this is corresponds to A, B and B. So first cell corresponds to substring A. So we'll see in the grammar which variable or variables could derive this substring A. So we can see that A can be derived by variable capital A. So we can put A here. So variable A can derive substring A. Similarly here also A. And here we can see from the grammar the substring B can be derived by variable B. so it is B here, and similarly here also we have B. Now coming to the second row, now we can get the set of variables from the previous row. So W12 means that these two cells together, AA. So from the grammar we can check whether any set of variables could derive AA. So if we see in the grammar, there is no set AA in this grammar. So this is 5, representing null. And coming to the next cell, W23. So that means in the above row, it is from W22 to W33, 23. This represents this substring, AB. So from the grammar, we can see that AB can be derived by variable S as well as variable B. So this cell can be filled by set of variables S and B. Now coming to the next cell, similarly 3, 4. So it means that the substring is BB, from 3 to 4, BB. So we can see from the grammar, BB can be derived by variable A. And W4, 5, it is again BB, so that is again derived by A. So now we have filled the first 2 rows of the table. Now when coming to third row of the table, we cannot directly take it from the previous row, because we have 2 possibilities for getting a substring of length 3. It can be taken from W11 to W13, or it can also be taken from this diagonal way. So here we are going to take, to find the value of this cell, we are going to take the variables that we have find from the above 2 cells, okay, and diagonal to this cell. So this we are going to write it down. So let me take, so what we are getting, A 5, and from here, from top to bottom, B, and the next one is S comma B. So from this we are going to combine this from left to right and find out a set of variables. So when A is combined with S, we get AS, and when AB, then 5 when combined, it gives 5 only. Now from this we are going to check in the grammar whether any of these is derived by the variables. So we don't have anything such as AS on the right hand side, but we have AB, it is present in the right hand side, which are derived by the variables S and B. So, and 5 is also not available. So this cell can be filled by variables S and B. So similarly, for filling this cell, we are going to take the above variables that we have found in this way, and diagonal to this. So the one which is above this cell, and also one which is to the diagonal of this cell. So how can we write that? A comma, let me write it here, A and then S comma B, and from here diagonal to this B A. So from top to bottom, B A. So now when we combine this, we will get AA, and then when S is combined with B, we get ASB, and when B is combined with B, we get BB. Now we'll see among these whether any of these can be derived by the variables. So AA, if we look into the grammar, there is no variable that can derive AA, so that is not possible. And SB, so again looking into the grammar, we don't have anything like SB on the right hand side, so that is also not possible. And finally BB, so BB is derived by variable A. So this cell is going to be filled by variable A. Now the third one, so now coming to this, so for this, finding this cell, we are going to take the diagonal of this. So we are getting BA from here, and then again BA from the diagonal. So when we combine this, we will get BA and AB. So from the grammar we know that AB is alone can be derived by variables S and B. So this cell can be filled by S comma B. So the process repeats for the fourth row also. So for finding this row, we have to take the variables from the above, all three, and then again diagonal. So from here to here. So what will we get? A phi S comma B here, and diagonal to this B A A. So again we are going to combine the first one with the last one. So we will get AA combinations, phi, it will give you only phi, and SB when combines with B, we can get SB as well as BB. So from the grammar given, only BB is derived by the variable A. So this will get A as the set of variable. And then coming to W2 phi. So now again this will also take the variables from here to here, and then its diagonal one. So that will give us A, then S comma B, then again B, and taking the diagonal one, we will be getting B A and S comma B, the diagonal to this one, B, A, S comma B. Now again proceeding with this, we get AS, AB, SB, BB and AB. So from the grammar we can see easily that both BB and AB can be derived by all three S, B. Now finally coming to the last row, so we have to take all these strings A, phi, S comma B, A, and then from the diagonal B, A, S comma B, S, A, B. So the combinations will be AS, AA, AB, then phi, SB, BB, SA, BA, and finally we have AA. So again here also only AB can be derived by S and B from the table, from the grammar. Now to conclude with this, we have to take only the last row. So if the variable set v15 contains start variable, then we can say that string belongs to